So this unit is the reactions in aqueous solutions unit. That's kind of what it's referred to as. And what you just did was a little bit of solution stoichiometry. I want to give you a few slides on what solutions are and how we can represent them in equations. So that's kind of the goal of these few slides that we're going to be going over here. A couple of things I'm going to show you are very common questions on the AP exam. And one of the things I'm going to show you is meant to be kind of the easy question on a multiple part question as well. So first off, an ionic solution is going to be referred to as an electrolyte. I mean, if you drink Gatorade, you're getting your electrolytes. Any ionic solution when you dissolve in water can conduct electricity because it has ions in solution. Ionic compounds can conduct electricity either if the solid is melted into a pure liquid, so molten sodium chloride can conduct electricity, although it'd be really hot, so it'd be hard to actually do much with that. But solutions, so put salt in water, there you go, it can conduct electricity. In Chem 1, we also went over the fact that metals can conduct electricity because those free electrons that are moving around. When you put an ionic compound in water, it breaks apart into its ions. This is referred to as dissociation. Remember, it breaks into its positive ions, the cations. How's it? They teach you that in some grade? The cat ions are positive. Man, just they're right with us. Anions are the negative ions. Actually, the prefix cat and an are used in other things besides just this. When we do electrochemistry in the next unit, I believe, cathode and anode are the same type of thing. Cathode is the positive electrode, anode is the negative electrode. Last term I have in this first slide is hydration. That when you dissolve an ionic compound in water, the ions dissociate, but then they get surrounded by water. That's referred to as hydration. We will go over the process of dissolving some more in the next unit when we start talking about the energy associated with that. Some ionic compounds, when you dissolve in water, it is an endothermic process. It takes in heat, so it also feels cold to your touch. Some give off heat, exothermic, so when you touch it, it feels warm. It all deals with how much energy is required to break apart the ions versus how much energy is given off when water surrounds it. Again, I give you 3 vocabulary words, not because on a test I'm going to ask you any of those 3 vocabulary words. It's just common language within the course, so you're aware of those terms. Back row has to bob and weave and stand up and down to look around and find this stuff, so I'll give them a minute. It's hard to see around Ethan's head. Sorry, Ethan. We ready? Right. Hey, precipitation reactions. That's something we should remember from Chem 1. On the far right-hand side of the screen, although my recording thing is kind of in the way, we gave you a solubility table. I remember in Chem 1, I referred to this as playing Battleship, where when you have a double displacement reaction, the cations switch to make 2 new products. Whichever one, cation, anion, comes together and hits a solid or an insoluble thing, it means you created a precipitate, hence the term precipitation reaction. Our textbook, I don't know if it even refers to it as a double displacement. It might just call it a precipitate reaction. When I gave you my gift over the summer, that nice big envelope, Soph, have you ever gotten anything that big in the mail before, that size of an envelope? You have? Yeah, I thought it was special, sorry. On the back side of your polyatomic ion sheet was a solubility table to remind you from Chem 1. Bad news for you is you do not get that when it comes time for the AP test. Instead, you just have to know certain things don't create precipitates. So first off, what is a precipitation reaction? It forms an insoluble product. That's why on the solubility table I gave you over the summer, it had I's and S's on the solubility table. I meant insoluble. S meant soluble, which is kind of confusing because S also means solid in phase notation. Actually, the one I'm showing you up on the smart board right now is probably a little bit better because it shows aqueous and solid. Recall that if it does not create the insoluble product, it is a spectator ion. I did say before that we are not likely to write a lot of chemical reactions in this class. That's just not what we do. However, the equations that we do write are usually ones that we get rid of the spectator ions for. So we typically will be asked to write equations, like given a balanced equation, now write the net ionic equation. I'll go over that in a little bit with you. Since a spectator doesn't do anything, it's very common for us not to write down those ions. My last point on this slide is not one that you have to write down. Instead, it's reminding me to tell you about this, so don't worry about putting this down. Since you will not be given a solubility table, you need to know some of the ions that don't create precipitates. For example, nitrate, NO3, will never create a precipitate. So if you see a chemical equation with two reactants and it's asking which one is the precipitate, it will not be the thing that ends in NO3. Alkali metals, lithium, sodium, potassium, they don't create precipitates either. So what's going to happen is you'll be given a couple reactants and maybe asked what is the precipitate created. And they're going to make it so it is ones that are fairly obvious. That, hey, it starts with sodium, there's no way it's going to create a precipitate because it doesn't have that ability to create a precipitate. Again, you guys could check your solubility table to confirm that. Sodium on the bottom, aqueous all the way across. So they try to give you ones that are kind of straightforward. For example, lead 2 nitrate plus potassium iodide is a very common double displacement reaction to talk about. One of the reasons why is they're two clearish solutions to begin with, but when the precipitate's created, it's this nice yellow precipitate. It really pops. It's one that we don't do in class, however, because I've tried to eliminate all lead from the chemicals that we use because lead is a pain in the butt to try to dispose of. So, don't write this down. There's three ways that we can write this equation, and I actually taught this to you in Chem 1 when we did double displacement reactions. You can write a balanced equation, you can write what's called an ionic equation, or a net ionic equation. The net ionic equation is very common to be asked on an AP exam. So what I'm going to do is, on the smart notebook, I'm going to do all three for that right now, to kind of show you. And maybe that's what you want to write down to remind yourself of something we did in Chem 1. Because that's the thing about AP Chem, first unit at least. We're a little bit of learn new stuff like you did today with Solution Stoic. We're a little bit of remind you of the stuff that you still need to know from Chem 1. Here's lead nitrate, PbNO3 Potassium iodide's Ki. They're both solutions, so I call it aqueous. When you see two ionic compounds as solutions in this double displacement format, remember the cation switch. So one of my products would be KNO3. Again, I rebalance the formula when I make that switch. That's why I'm not calling it KNO3-2. My other product is PbI2. If the first step is to try to write a balanced equation, this is not balanced yet. Because I have a 2 nitrate on the left-hand side, I'm going to put a 2 nitrate on the right-hand side. But now I have 2 potassiums on the right-hand side. I need 2 potassiums on the right-hand side. I'm sorry, the left-hand side. Now it's balanced, but I don't have phase notations for the products. Okay, ladies and gentlemen. Which product is the solid? Yeah, the PbI2. Nitrate compounds never create a precipitate. Potassium, alkali metal, never creates a precipitate. So there's certain things that you can hopefully do to know that. And I think this problem is, in my mind, and probably in College Board's mind, a very simple double displacement reaction for you to identify that. Because you have two things that would never make a precipitate together as one of the products. In Chem 1, we then talked about the fact that when it says aqueous, really what that means is there's ions floating around in solution. So if I were to rewrite PbNO3 in an ionic equation, I'd have Pb 2 plus ions and 2 nitrate ions. If you wrote Pb plus 2 instead of 2 plus, it doesn't matter. I know in Chem 1 we actually usually say plus 2 or plus 3 instead of 3 plus. There's a difference between representing an oxidation number and an ionic charge. In the ionic charge, one usually puts the number first, then the positive or negative sign. When I had to take a course on teaching AP Chem, I asked my instructor, do they care? And she said no. She said some people don't even put down charges in an ionic equation. That's what the graders care about. And if it's an ionic equation, you should show ions. 2K plus 2I minus yields 2K plus 2NO3 minus. Both of those are aqueous. Sorry, I'm running out of room. I'll write my final product on the bottom here. The precipitate does not break apart. Because it's not aqueous, it's not ions floating around in solution. A balanced equation is actually a simplification of what's happening. This is a better representation of what's happening in that reaction. I have 4 different ions that are all floating around in solution to start with. 2 of them are going to attract to each other enough to create a precipitate, something that is insoluble. If I can move that up to help out. If this is the either total ionic or overall ionic equation, the net ionic equation is what is commonly asked for on AP tests. Where a very common AP test will give you the balanced equation on the very top here, and then part A will ask you to write the net ionic. The net ionic equation is referring to which ions made the precipitate. So you're omitting spectator ions because spectators don't do anything. In this particular one, it'd be the lead 2 ion, the iodide ion, making PbI2. And you will learn in this class that we can actually use that net ionic equation in stoichiometry. So we don't have to have a balanced equation, we just have to have an equation that has stoichiometric coefficients. I mean, there's a 2I in front of there, there's a 2I in front of the original reaction as well. It works either way. I have 2 slides left, but that deals with single displacement instead. And I think what I want to do is stop here, and I can go over the single displacement one next time. And that way we can get into the lab bench for the last 10 minutes. Okay? So